And it's time for the last discussion of this week, and I give the speech to Jörn, who is on site, and Sarah, who is online.
All right, so Jörn, are you going to be manning the slides, or I just see Pop.
Because Pop had problems managing the slides.
There you are. Well, anyway, thanks again, Pop, for letting us use your computer. And hi, everyone. So as you see, I'm online and Jörn is in the room, and we thought we would sort of distribute this. We have a few slides. We're not going to give long talks, but we wanted to maybe introduce the discussion. And so, as you know, we did a survey. And maybe we could start by just looking at some of the reactions that we got. So we probably got about a third of the participants reacting. So thanks a lot for those of you who did. Maybe this is a bit skewed towards the younger generation because of tools like Google Forms. We'll have to see, but it's a pretty good demographic spread, and we grouped ourselves into the old and oldish farts to cause no offense. However, you can see that there's quite a lot of young people, at least, who reacted, and it also shows, and I think this is great, that this is a young and active field, right? It's you know, I've been to certain fields, especially in like certain areas, let's say more like cosmic ray physics, where it has a very different demographic spread, and so. We had this idea partly that we wanted to discuss consensus of like how the field is evolving in terms of what people used to think about X-ray binaries and what they think today. And part of this was inspired by a meeting that many of us in the old and oldish farts category were at ISI in 2008, where we sat in a room and for a week we tried to discuss what we actually agreed on. And we made this plot that was in, I think, a Proceedings article. And as you can see, we made this hardness intensity diagram, and I highlighted in red here the areas where we thought we had consensus, which probably people wouldn't necessarily agree even today. For instance, especially around whether or not the disk is recessed, we were pretty darn sure that the disk was recessed in the hard state and then moving into the ISCO by the time of the HIMS. The QPOs are a bit interesting. You know, we talked a lot about type C in the soft state and not in the hard state. And, you know, you could just see there's some differences there. And so we thought maybe by doing this poll, we could kick off a discussion on what we can and cannot agree already and where the progress has to go. So starting with, can we agree on what a microquasar is? In fact, no. It looks like there's quite a lot of different opinions here. And we just showed the demographic spread a little bit. I mean, the majority of people seem to be split between it having to be a black hole or a neutron star black hole. People are not so crazy about starting to be inclusive to other objects like white dwarfs. But there's some interesting other notes, including saying microquasars is an outdated terminology or a good term to popularize black holes, which I think is also quite on key. So let's keep going. So then what we did was we made a word cloud and we split the reactions. We tried to find a sort of year that roughly split the group. So I hate to break it to you guys, but anyone who has a PhD before 2015 is officially old now, according to these demographics. And so we have the before 2015 PhDs and the after 2016 PhDs.
This includes you, Katja. This includes you, Vicky.
I know, poor Vicky, and I think Elise, right? Also, but anyway, welcome to the club. So for those of you who don't know how these word clouds work, you basically just copy all the words into this program, and the size of the word represents how many times it came up. So it gives you a little bit of a sense of whether there's strong clustering. And the news here seems to be that there's not a lot of consensus on consensus. So we see a lot of words coming in, not a lot of words really dominating. And more or less, words like the disks and states come up. So I think people agree that, in terms of at least where the maybe thin disk and the soft state, what the states actually mean in a rough sense, seems to be there's some consensus. I thought it was interesting that among the younger group, the word QPO came up quite strongly, and also jets came up a little stronger in the younger group. But overall, there's quite a widespread. So if you want to go to the next slide. Now, if you go to no consensus, there's a lot of consensus of what we don't know. And it seems to be, not surprisingly, clustered around words like geometry, corona, winds and jet, QPOs. And so I think, and one thing I'll point out that I think is also interesting is that the word launching and, relating assumedly to jets and winds came up pretty strongly in the older crew. And mechanism was the word used in the younger crew. Maybe that meant the same thing. So it's a little hard to analyze, but overall, I think this is where our discussion is going to go. And if you go to the next slide. This is also interesting, right? There's a huge amount of excitement of a wide range of things to study, but there were some differences between the older and the younger groups that I thought were kind of interesting. The word polarization came up much stronger with the older group. And then you can see that in the younger group, there's a lot more emphasis, for instance, on like reflection comes up, also jet launching. Simulations and models were pretty strong wording. Yeah, so I think, that's something we're thinking about is like, why are the younger groups thinking a little bit more about maybe reflection and looking a bit more towards the theoretical side? Whereas in the older group, I was a bit surprised that there was so much more spread overall and a bit more emphasis on polarization. Anyway, okay, so moving on. I think it's pretty clear that the biggest question is in the geometry in a lot of sense. How do we go from this cartoon view that we maybe had a little bit more on the left to the types of views we're getting from more theoretical types of simulations, where we really try to understand the dynamics and the microphysics. And this is just flashing the slide that Matthew showed. And of course, what we find is that the whole region seems to be threaded by magnetic fields, which leads invariably to flow. And one of the things that I do see some consensus on, which is fun, is if you go forward, Jörn, there used to be this kind of Game of Thrones camps in the field between, I would say, jets and disks. And what is really happening is that the people who traditionally work more on jets are moving inwards and thinking about the corona, and the people who have been traditionally thinking about isolated corona are now working a little bit more on jets. And I think that is really pointing the way to how things are going to have to go. So yeah, I think Jörn is going to take over now, right? Mostly for the discussion. I'll help with some of the moderation, but these are the points that we came up with based on your inputs. And I'll try to man the Slack and the Zoom for questions. Go ahead, Jörn.
Okay, so in general, I think if one wants to summarize this week, I think we can see 2.5 type of streaks. I think there's a lot of really interesting work that was done in the past years, either since the last microquasar workshop or also over the past decade on many of the detail questions that we have in the field. They essentially center around 2 areas, the accretion physics of flows, right? A lot of the work on microquasars really is studying the physics onto compact objects, rather than studying, say, what happens close to a black hole, and then also on properties of black holes and on the black hole population, especially also with the work that was done, for example, on ULXs that we heard this morning. So the big questions that are still open, and this is definitely only a selection, is, for example, what is this corona? Personally, I hate that term because I think it's completely misleading. So I think what produces the power law really? Is it a thermal distribution? Is it something else? Is it an outflow? Are there bulk motions in there? Where does this cutoff come from? The problem here, I think, and I guess we can discuss this also further in the discussion, is that if you look at the spectra of microquasars in the X-rays, it's essentially a power law with an exponential cutoff. So whatever physical model you can invent that produces something that is a straight line in a log-log plot that kind of turns over will also fit a black hole model. So the predictive power of many of the physical models is probably not as large if you just look at the spectral shape. So the big question then is, how does this relate to lags and timing? Do we see features really that have something to do with strong gravity, like lens tearing precession in the QPOs? We now also see timing in other wave bands, which is interesting. And we've seen this relationship between winds and jets, and also the relationship between jets and whatever produces the X-rays. And so we've seen a lot of amazing talks about this. I think what we've seen less are attempts to put all of this information together. This has been a problem for a while. I stood here in the last Microquasar workshop meeting and said the same thing. I still believe that this is true, and I think we really in the field need to change something. I think what comes now more stronger also is the ability to measure black hole properties like spin measurements, with a lot of the caveats that have to do with the flow, with the flow physics that we don't get so much, and also with gravitational waves and how the gravitational wave sources, which by some sense are also compact objects that have roughly stellar masses, how that relates to the objects that we are looking at. So the question really is, where do microquasars fit in the overall field of astrophysics? So what can we do in the next years? And that's also, I think, something that we as a field need to think about a lot, is we will be getting new observational tools. On the other hand, also observational and theoretical tools will disappear. I think overall the situation is a bit better than the flat earther here in our meeting, who ignores time zones, Greg Sivakov, seems to think. I think multi-wavelength campaigns will become easier because we'll be having a large number of facilities in other wave bands, and this overall trend that non-X-ray people have now realized that time domain astronomy is interesting, I think will help the field from the radio over the optical and the ultraviolet. We'll be getting better diagnostics of the inner accretion flow through the next generation of X-ray missions. XRISM will be very exciting for the studies of winds. We also heard a lot about polarization that will require a lot of work from us, I think. And there also will be missions that we didn't hear so much about, like SWAM or also the Einstein probe. The problem will be that there will be little to no data available above 10 kilo electron volts, and that's something that I think we as a field will suffer from. On the other hand, the techniques will become better. Fast VLBI, X-ray spectral timing, I think we've seen really has made progress over the last years. And polarimetry will be absolutely amazing and blow everybody here in the room away, because it's so much more complex than anything that we thought is complex, that it will be really, really fun for everybody. And finally, obviously, the modeling has made big strides forwards. We heard a lot about that CPU time is a problem. You always hear this from theory, but if you look back 10 years, nothing of the more advanced simulations that we saw here could have been done. So this will also be amazing. So I think there's lots of potential, and we as a community need to collaborate and work on this. We need to emphasize much more multi-wavelength work, and even a tighter collaboration between theorists on the one hand, modelers on the other hand, to bring all of these pieces of the puzzle together so that we see the forest and not the individual trees. And with this, I would like to open up this for discussion. Did we miss something here? What do you think we should do as a community first? And where should we go? Or should we go in a completely different direction?
Jonathan Ferreira was the first with his hand up.
Thank you. Well, in a way, I will be more optimistic than what has been said just now, a bit like Sarah said. I think now, from what I've seen the whole week, all numerical simulations were including large kilomagnetic fields, actually. And it turns out that, at least to my eyes, most of them had the same results, more or less, which is like the Charcot-Sounieff disk doesn't exist at all, right? We didn't see this anymore. You have always winds. We have buffy disks. So the concept of alpha is dead in a way. So you have unavailable winds always, and radiation is really important, of course, for spectra and modifying a bit, let's say, the vertical stratification of disks. But if you compare like the nice simulations of radiative MHD, NGR MHD simulations, and our own in non-relativistic, the vertical structure is about the same. So, well, it seems to me there is a consensus actually, and the jet now, from observations, we don't see the spine or the Blanford-Snezek. We see some kind of interaction which takes into account the disk. So there are still questions, of course, and that's great. But it seems to me that people doing dynamical simulations need to provide more synthetic observations. And I think that what Chiara and collaborators want to do is great. But also observers need to be more, in a way, aggressive with respect to models. They need to ask more of them, because if a model is only addressing, let's say, QPO, but there is no global picture, then it doesn't work. And if a model provides only a CD and doesn't address QPO, it doesn't work either. So we need also to use probably more better words, like, for instance, a corona indeed says nothing, but a MAD, for instance, is not arrested. So I'm not sure if we don't use the correct words, I guess the mind doesn't work well as well.
So Jörn, I can't see the room, but there's quite a few people on Zoom. Do we want to go back and forth?
The room needs to decide whether it wants to ask questions. So let the Zoom take over until the room is provoked.
Okay, in order of hands, then the next one was Federico.
Everyone, I just wanted to say that I agree totally with the fact that Jörn said before, that we need a more holistic picture and we need to do more multi-wavelength or joint observations. And what I was just thinking, like at the last Microquasar workshop, I presented only one result on a multi-wavelength dataset, and now I'm presenting 3. And that's because now we are increasing a lot the number of multi-wavelength observations, probably after V404, and probably also with the help of NICER. And we are also getting better in coordinating in general because we are just learning. And so I think now we can actually start to do this kind of joint X-ray and optical and infrared and modeling together, while before it was not really possible, I would say.
Yeah, I think that's a good point. Yeah.
Yeah. How are we doing in the room, Jörn?
I'll say something when the room says something.
Okay, so Zoom wins, then it's Greg.
So one of the things that I've begun to see is that we talked about this, jets and out and winds. And I think another way we're going to go forward is really working together and talking just, instead of jets and winds, talking about outflows. I think this will, be something that may lead to greater collaboration between more people and addresses a fair number of some of these issues that are on the screen. Said as a jet person.
Yeah, and I mean, just one little note on this, and also what Jonathan was saying. What's interesting is you can have the same underlying dynamical structure, and just depending on where the electrons get heated at any given time is what you're going to see. So sometimes you might see a faster outflow versus a slower outflow, depending on where the dissipation happens. That's something we don't have a good handle on, but it might be much more unified than we think. Okay, so unless I hear otherwise from Jörn, then Phil is next.
Yeah, thanks. Yeah, so I think one of the things I've really noticed from this meeting as well, and just generally in trends, is there's 2 effects. One is that I think with the understanding the X-ray data, there is this at least attempt now to start modeling things in terms of timing, spectral timing, right? And that's new in the last few years, that not just that people haven't been thinking about it, but more that people are starting to build models. And of course, that's crucial because, you know, it's only by comparing models and doing fits and doing statistics, right, that we can test things. But the other thing, of course, is it's driven by this, coincidence with I think the simulations now becoming good enough and the people starting to think more about, the role of the magnetic field. And so, you know, there's some hope that they can kind of merge with these models as well at some point. But of course, don't forget the data that to a large extent, a lot of this is driven by, for example, NICER, right? With just this abundance of amazing data for X-ray measurements of bright sources where you have spectra that aren't distorted anymore. And so one of the consensuses that seems to be emerging is that at least this corona power law emitting region has some kind of vertical extent. And the debate is largely to what degree that is, you know, how big that is, right? Which kind of depends on then your interpretation of the lags and also the spectral fitting and degeneracies and stuff. So it's quite I mean, I think it's moving in a much more sort of rapid and I think in a good direction than it has been, I think, for some years. And that's just driven by this coincidence of different effects.
I agree. And if I may add something also related to another comment that I made during the meeting, I think it is really crucial that people also make their tools available there, because the data sets are becoming more and more complicated. And I think we'll have to work more and more in larger groups and also share our tools and not only make data available. I think NICER is doing a good job there already, but we need the same also in other wave bands. How many more people do we have, Sarah?
Well, we're coming back to second rounds now because I see Greg's hand. So no one in the room has anything to say?
No, the room wants to go to the beach, I think. No, yeah. Now people are coming from the back. Thank you. You're saving us here. Matteo.
I was just wondering, is anyone trying to compare our stuff with, for example, protoplanetary disks, to be super holistic about that? Is there a major problem in doing that? Are there interesting things that might come out from that?
So I've tried talking with a few of the German planetary disk people, and there was not so much interest really in collaboration, because that tends to be dominated by problems of dust and things like that. I hope in other countries that this will be better, but I think a related question to this, which I have to say annoys me a bit more, is that we also as a community don't have enough exchange with the AGN community, right? And I think that is stopping both communities, because we are probing essentially the same type of flow with a relativistic object in the center and so on, but on different timescales. And I tend to believe that we really need to understand both systems at the same time. But Pop has a comment? Or Jonathan?
Yeah. Yes, sorry. Yes, actually, I was following what's going on in Young Stars and also the new ideas that came up. And as you said, there has been a huge focus on a non-ideal MHD because of the fact that the protostellar disks are not enough ionized, at least in the region of interest, the region where you need to form planets. But it is clear also that very close to the star, it is ionized enough, and very close to the star, so it's ideal MHD, exactly the thing we do in X-ray binaries or AGN. And close to the star, we know there are jets coming in. And there has been a huge debate for years, for many years, whether the jets, the optical jets that they were seeing, you know, the fast and powerful that go very far away from the star, they will be driven by the star, or the disk. And it turns out that there is not enough power. It's very hard to also explain the mass loss rates that are observed in jets if you need to, say, anchor your large-scale magnetic field, because also you need them into the star. So the consensus now is more that it's coming from the accretion disk, the inner regions of the accretion disk as well. And as I said, the Zhu-Stone 3D numerical simulations showed the same structure as what we see in GRMHD simulations. So, well, I would say there is some kind of consensus in terms of dynamics.
Thank you very much for this. It's now 1:30, so this is the official end of the discussion.
Well, we have 5 more minutes. We started late, actually.
Okay, then there's Anjay who wants to say something here in the room.
So Jens, thanks for your comment that tools should be made public. I just have a, I would like to appeal to the group using the high density version of Wi-Fi-on-X to make it public. The first paper from that code was published in 2018, and people still publish results which I'm personally not able to test. It would be great if it gets public similarly to RELSTIL. Thank you.
Okay, Nick Kulaf is here. Is there somebody online, Sarah?
No, I mean, I'm manning the Slack a bit, and there was a comment that I thought was interesting from Greg. We were discussing about, the AGN community, because you made the comments about that being important, and the fact that, we tried and the AGN community sort of ignored us for a while, but actually changing look quasars is a good point, that this is starting to take the notice again and the comparisons with state changes. So maybe somebody wants to elaborate on that?
Yeah, so we have Nick here. I don't think he's going to talk about this, I assume.
Oh, sorry. Okay. I have a request to the people who do GR-MHD simulations. Most of us cannot follow them. So the request is to please try to explain in simple physical terms why should we believe these results? Just because we have a result from a GRMHD calculation does not mean that it's nature. Several assumptions went there, and the result of the assumption is what we see. So it really helps. It will help a lot to improve our cartoons if we understand what the simulation tells us in physical terms. So it's a request, and please think about it.
Perhaps I can say something about that. So we just got funding in Germany for a group of people who do GRMHD simulations for blazars, VLBI observations, and also some X-ray people. So we got 3.6 million euros for 10 people overall to work on this, on something related to that. So both doing GRMHD simulations, comparing them to VLBI, but for example, we will be doing in Bamberg ray tracing to combine these simulations with reflection. It's mainly method development, but I think from the point of view of bringing these communities together, I think there are some efforts going on at least. And I'm hoping a bit to convince these guys that the small little systems are also interesting. Sarah, anything to add?
No, I mean, I think this is really going to be a good way forward, but the caveat, as always, and I agree with Nick, actually. I think that, as somebody who is working with both semi-analytical and simulations, it's really important to always benchmark your simulations, understand what you can and cannot say, and remember these caveats, like the fact that the microphysics is still something very much up for grabs and will change drastically your conclusions. I mean, people read the EHT papers, and actually, a lot of people didn't realize that the biggest contribution to the error on being able to test GR was based on our lack of understanding of the electron heating. So, it's something where that level of understanding at the, sort of kinetic side is still where, as long as we don't have that really well understood, we're going to be limited in whatever we put into ray tracing or other types of simulations. It's not the be all and end all. Jerome wants to add something.
Yes, sorry, it seems that since I'm logged twice, I can't raise my hand. Well, it's a bit to answer or to comment on the discussion on the Slack. Maybe it's a very naive or very stupid thing I'm gonna say, but if we can't get closer to the AGN community, why don't we try and get closer to the GRB one? Because of course the central engine or the beginning, the triggering of the disk and the ejection is not the same. But as Rob showed in his talk, they have much elaborated models for the acceleration, for the jet, for the production of gamma rays, and so on and so forth. And actually, I think being quite a little bit in touch with them for Swan, but I think they managed to try and have some observational projects being built and that are going to be launched. There is SWAM, of course, but there is also Einstein probe. There were a lot of activities around Theseus that was not selected, unfortunately, but there's a community there and they're trying to work together. So maybe that's something we could look into.
Good point, I think. Okay, there are no comments here in the room.
There's one last one from Greg, it looks like, on Zoom.
Yeah, I didn't want to be the last person to comment at the conference, but I guess I'm fairly loud. So on the point of other requests for theorists is, as we see X-ray spectrotiming and basically general spectrotiming spread, not just within the X-ray community, but throughout for the optical IR labs, for the radio millimeter, whatever, what's really useful for us observers in order to get time are these models that make any type of predictions in this regime. So when looking at your GRMHD codes, we're trying to analyze these things. Anything you can do that will really reinforce the importance of this spectrotiming regime will be very much appreciated.
Thank you very much. These were the last wise words of the conference, I guess, by the person who doesn't seem to have to sleep. So thank you very much for this. I think let's close the discussion session at this point. Thank you.
Yeah, thank you, Jörn and Sarah. Thank you everyone for this morning sessions and the one from the previous days. So as I said earlier this morning, we will put the vids on the YouTube channel as they arrive and are processed. And I think before we can all go to rest and do whatever science and other things maybe, there is a very, very, very last announcement that is to be made by Nick Kilafis, I think.
Yes, I do have an announcement. But before that, I wanted to make a comment. Think of a pyramid with a triangular base. It has 3 points on the base and one on the top. Clearly, on the top of this pyramid is Elise, and she did an excellent job, and we thoroughly enjoyed the conference. Thank you very much, Elise. Looking at the base of the pyramid, I see 3 names: Victoria, Jerome, and Pierre-Olivier. I think they also deserve a smaller thank you. And the announcement. The other day, Pierre-Olivier and I were talking, and the comment came that the previous microquasar meeting was in Porquerolles, west of here, and this one is in Sardinia. And smiling, Pierre-Olivier said, "It looks as if it's going east. Why don't you organize the next one?" And I said, "Yes, I will, in Crete." So I will see you 2 years from now in Crete for the 10th Microquasar Conference. It will be either in late May or late September, so that we can have good rates at hotels. Otherwise, it's too expensive because Crete is very touristy. Next year, we'll circulate question, whether you prefer the May or the June. I know the American colleagues prefer end of May because in September they have classes. The Europeans may not prefer that, so we'll see. The majority will win. In any case, 2023 in Crete. Okay.
Perfect.